This is the last section of the AP Stats course. So this is 12.2, transforming data in order to achieve linearity, which provides us with a very good opportunity to review linear regression, which will be incredibly important on the AP test. Sometimes when you graph your data using a scatter plot, graphing your explanatory variable versus your response variable versus your explanatory variable, you notice that it's not linear. And that's when we can go to something called the ladder of power, and we can transform either the x or the y. Typically, it's easier to look at if you're transforming the y. But if you, for example, if I were to square all the observed y values, then I would be using a power of 2, and I would have a model that involved y squared. And you can see that there's this list, squared, square roots. We can also use something called a log, and if we take the log of a side, that's a very powerful tool that can turn something that's logarithmic or exponential into something that will then look linear. And so basically we look at the graph, we want it to be, we want it to look linear. When we see that it doesn't look linear, we use guess and check, and we try modifying either the x or the y, and then we graph our modified x and y and look and see if it's linear. And when we run the linear regression, we can look at the R value, which is our correlation coefficient, and we can see how well we think it's fitting a linear model. And we want to have a very strong R, and we want to have the appearance look linear, because remember, the only way to know if something's linear is to actually look at a graph. And then if you take the logarithm of both sides, both the observed x and the observed y value, then you'd be doing something called a power function. And you would be either doing a common log, which is a base of 10, or a natural log, which is a base of e, and doing that to both the observed x and y values. I'm going to share with you a cool article I found that relates light density coming from a country and compares that to their GDP, or gross domestic product, and how we can make predictions from this. And it's a power function where they did the logarithm on both the observed x and y values. And how can you tell if you need to do something like that? You look for orders of magnitude change in your observed x and your observed y values. Like if you go from 3 to 300 and then to 10,000, those are orders of magnitude, large changes. And those kinds of changes are usually better represented using logarithms. Your calculator has two functions, exponential regression and power regression, that are built into them. You can find those in the same menu as linreg. And these can help if you have a model and you know that you need to transform it using a log or natural log on one side, meaning just the x or just the y. Or if you had a power regression, you wanted to transform both the x and the y, you could use these exponential regression and power reg to do these transformations on the original data. The calculator will transform it in its little calculator brain and spit out a model that would relate these two things using a logarithmic relationship. And the calculator, what it's doing is using some of the properties of logarithms to write its models, because we know that logarithms are actually exponents. So if you have a multiplication in an exponent, you're actually, or if you have multiplication in the real world, you have addition as an exponent. So it's using basically those properties. And if you have a power of a power, then it's really, you can see that you can bring that power down in front of the exponent, because so like x to the p is now p times the log of x. But the problem with the exponential regression and power regression is that you won't be able to check your residuals. So it's important to be able to transform your data yourself, because you want to be able to check your graph and say, does it actually look straight after you've done your transformation? If you're going to prove that you've actually met the linear, LINER conditions of linear regression, you would need to be able to do the transformation yourself and run that linear regression on your transform data, because the only way to see if something's linear is to actually look at it. And that would check the L condition from linear. And we could look at the R value from the linear regression to see the strength of this fit to the model. By creating the graph of the residuals, we can look for that equal scatter of the residuals, and that would check the E condition. So if we're going to meet those conditions, the look of the graph shows us the L, the scatter plot of the residuals versus their X values. That's going to show us the equivariance, equal scatter. Taking those same residuals and creating a histogram for to looking for that symmetrical bell shape, looking for no outliers, looking at the normal probability plot. That's going to fulfill our nearly normal condition. And then, of course, we want it to be independent and random. And that would fulfill all the conditions of doing linear regression. And in theory, you want your residuals to be as small as possible, because that standard deviation of your residuals is a measure of, on average, how far off your model seems to be from the observed values. You don't want your model to be off by a lot in your predictions. You would ideally want a model that predicts really, really well. And since S, standard deviation of residuals, is kind of your average prediction error, that's important to look at that number and realize that that's how far off you seem to be. And basically, we just look for, with guess and check, we look for what transformation seems to be getting us to the best model. So I'm going to go to the calculator and put this data in the calculator. I'm giving you, to save time, I've given us the hint that this is going to be a cubic situation here, where we're trying to predict. We want to give a prize for the biggest fish. And so I want to know, is there a way that I could take the length of my fish and then automatically be able to tell the weight of the fish to find out which one is the biggest fish? So we're going to check this data. We put it in our calculator. I already have it in my calculator. And when I start off with my scatter plot of my length on the x-axis and my weight on the y-axis, I can see a clear curve in this data. I don't see orders of magnitude changes in the values, so that's giving me an idea that maybe a squared or a cubed situation, or a square root or a cubic root, would probably be something that might straighten out this model. So my next step will be to just try things and see what this transformation could do. So now what I'm going to do is I'm going to try using a cube. So I'm taking my observed y values and I'm cubing those y values, and let's see what this graph now looks like. I haven't changed my x, so I need to keep my x on in L1 is my x-axis, but now I have cubed for my y list, and let's see what that does to our graph. And so when I go into the graph, and I need to zoom stat so that I can see it, and this cubing of the observed, you can see that now the curve is actually it's steeper. So that was the wrong direction to do. Cubing the observed values was not a good idea. So instead, I'm going to revise that plan and try the cubic root. See how this guess and check? Guess and check happens where you try something, you look at the results. Did it get you further away from what you wanted or closer? Okay, I've got to zoom stat to be able to see this. And now you can see that this taking the cubic root of the observed y values did a very good job of creating a graph that looks straight. And the only way to tell if it's appropriate for linear regression is to look at the graph and see that it's straight. So now that I see that the data looks straight, I'm going to run a linear regression on this data. Remember, you have your x values in L1, and you have your observed values that have been transformed in L3. So I need to use L1 and L3. And I run my linear regression, and I see a very nice R value of 0.998785. So that is a very strong R value, and it's nice that the look was straight. So that is a good indication that this would be a great model of our data. So our L1 versus L2, just to summarize, it was curved. So that told us we had to do a transformation. We tried an L1 versus an L2 cubed, and that came out more curved. But when we tried L1 versus the cubic root of L2, we saw something that looked very nice and straight. Now, just as a matter of course, it would probably be a good idea to also check what if I had transformed the L1 instead of the L2 using this same cubed situation. So that would be another thing that we would want to check. So now if we want to look and see if if we switch the relationship, that maybe it was a cubed on the observed x value versus the non-transformed observed values in L2. Or should we take a cubic root of the observed x values versus the non-transformed L2? Now, since we just saw that it was making it straight with the cubic root on L2, that would be the cubed L1. Those would be the ones that are related to each other. So I'm just going to go with that one to look at, because that's the one that's going to look somewhat straight. The other one is going to have become more curved. So, okay, so in my L4, let's put the cubed x values. So I'm cubing L1 and putting that in L4. And then now what I want to do is I want to graph that. That's my new x value though. So I need to have my x list is my transformed cubed x values, which is in L4. And this is going to be against the not transformed L2 observed y values. So when I graph this, I see something that is going to, it looks fairly straight. Now, which one was better? Was it better to cube my x's, or was it better to take the cubic root on my y's? How do I know? I have to run a linear regression. So I run linreg, being very careful to tell it where's x now. I'm using transformed x's. They are in L4. So I'm going to put my L4 in, and that will be the x. And remember, I want to use the not transformed y. So those are the L2, and I get a new equation. But in this equation, the r is slightly lower than I had with the cubic root on the observed y. So I'm just going to write that down so that we have that the new r is 0.9976, and I did see that it was straight. And this would be a fine model for this data. However, the best model that I was able to find was using L1 versus cubic root of L2. Now on the AP test, like probably either of these cubic models would have been fine, but the best one is the one where I have L1 versus the cubic root of L2. So now that I have a model that I feel is the best model for this situation, I'm going to go through my conditions of liner, and I will write out graphs to support my checking of these conditions. And so let's go through this data and see what it would look like to go through all these conditions. So first of all, I know that it looks straight. I have, going back to my data that I think is the best model, I'm going to go back to putting L1 in my X, and I'm going to put my L3 is going to be my transformed observed values. But in order to get my residuals, I'm going to need the equation. So let me just run this again to get my equation. So L1 versus L3. Okay, so running this linear regression, remember I'm going back to the observed x values are in L1, the transformed cubic root y values are in L3. And so now I can write out my equation with my slope of 0.2466157711, my y-intercept of negative 0.02203997075. So I'm going to use these numbers and put them in model form. So putting them as the model, I have to remember that I did the cubic root on y, so I need my model to show that when I'm writing it out. So my y-axis was the cubic root of the weight. My x-axis is the length. Just going to quickly do a rough graph of my data. This shows that I actually did look at the data to verify that I had a linear relationship. Of course, I had to do the transformation to get this relationship, but I was able to get a linear relationship. And then I want to put some numbers on the X and Y axes just to show that I have some values to give some context to the reader. And thinking about the form, direction, and strength, the graph of the length and the cubic weight is very strong. And I mean, it's very strong. Look at that R value. It's positive. It's linear because I can see that relationship. And I'm going to write my R value just to support that value, 0.99879. That satisfies the linear, it being linear, which of course you would never do linear regression unless you had something that was linear. We need it to be independent. And I would say that the 20 fish that we caught, probably there are more than 200 fish in this lake that we're fishing in. Now, in order to check the nearly normal condition, I actually do need the equation. And because I need to find the residuals, and these residuals are going to be about being the cubic root. So my predicted cubic root of the weight will equal negative 0.02204 plus, that was the y-intercept, plus, now I'm writing the slope, 0.246616 times the length. And so I have to put this equation into my calculator. I will put it into the calculator in order to find out what the residuals are. I will have to take my L3, which has my transformed weights, and I'm going to get my predicted weights, transformed weights, and I'm going to have that be in L4. So going to the calculator, putting that into L4, I'm going to enter the equation that I just wrote. There's my y-intercept plus the slope times, and remember where you have your x values. We are using the L1, the non-transformed x values. And so we can see what our residuals are. And these residuals are residuals for the cubic root of the weight. So L3 minus L4 gives me my residuals. And so then now I need to graph these residuals against the L1 values, which I didn't transform. So let's go in and do a scatter plot of these, because I'm going to look for this equivariance. And now that I can see this graph, there does seem to be a little bit of a pattern to these residuals that seems to have a going from positive to negative as you move from left to right. You can see that there's it like goes above and then it goes down below. But the values are really, really small, and combined with the fact that the R value, the correlation coefficient was so strong, I'm going to go ahead and also look at the histogram for these residuals to check the nearly normal condition. Um, I, I think that we're going to find that the straightness of the overall system, the strength of the R, there's only 20 values that we're looking at. Now you can see the histogram for the residuals. It looks so good. This is more evidence that even though maybe there's a slight pattern of in these residuals, I'd say because they are small, that's good evidence that we can continue. So I'm going to just check really quickly to see if there were any outliers, because if there were outliers, that would be a clear violation, but I don't have any outliers according to the 1.5 IQR rule that I can observe using a box plot. So I don't see any outliers. And now the most powerful check we have is to check the normal probability plot for these residuals. So if that is looking reasonably straight, then I think we're going to say that this is an appropriate model for predicting the weight of the fish. And I would say that this normal probability plot does look fairly straight. So let's put this information onto the paper. So we're checking for the equivariance. Oh, wait, we put those residuals, by the way, we put them, the predicted values were in L4, and the residuals, actually, we got those in L5, just to remember. But anyway, we're checking that equivariance condition. So we would draw a graph to show what we saw as best we could with a little bit of a scale. There's only 20 values. This does look reasonably enough like chance scatter. I don't want to contradict myself and say that I see a clear pattern, because that would be evidence against linear regression. But I think with an N of 20 and looking at the other things that I looked at, like the normalcy, I would say that that equivariance was satisfied enough. So now I want to generate some graphs supporting the nearly normal condition. And that's the histogram. I looked at the box plot to see that there were no outliers, and I'm going to draw my normal probability plot to show the straightness of that. And that's going to satisfy the nearly normal condition for inference. So now that we've decided that this is a good model that predicts the cubic weight of our fish based on some length of the fish, you might be asked to make a prediction, either using a length, what would the weight of the fish be, or using a weight, what would the length of the fish be? So why don't we use this model to predict the weight of a fish that has a 30 centimeter length. So can we use this model to predict the weight of a 30 centimeter fish? Yes. So we're going to, because they gave us the length, we're going to put the length into the algebraic equation, into the length input, and I'm going to solve then for the weight. You'll need to be able to solve a variety of algebraic equations, including ones that involve logarithms. So putting that 30 centimeter fish in, then I get a cubic weight of 7.37656. And what I need to do now in order to solve for the weight is I need to cube both sides. So I'm just writing the workout again. Now what I'm doing is I'm cubing, and because a cube is going to cancel a cubic root, and so when I do that, I get a weight, predicted weight. Make sure you put your hats on things. I get a predicted weight of 401.3 grams. And I feel fairly confident about using this model for the weight of a 30 centimeter length fish will be 401.3 grams. I feel fairly confident in using this because this is within the domain of our lengths and therefore is not extrapolation. So that seems pretty, it seems like a good way to find the weight of the fish and therefore be able to give out the prize money. Need to be prepared to put a weight in also, and to be able to solve for the length. So you do need to be prepared to use your algebra skills to do that. Now, this second example that I'm going through, this is looking at the number of transistors for a certain year, calendar year. Now, I see that these numbers of resistors starting at 2,250 and then growing to, well, let's see, 2.3 million. So like 2.3 billion. So that is a huge jump in order of magnitude. And this is something where it's pretty clear that a logarithm would be the way to go to transform the transistors. However, the calendar year does not seem to need that. Now, frequently, when you're using transformed linear regression, they're going to give you Minitab output. And this model, they say, well, it's a natural log of y. So they did do the natural log of the transistor number. And they are using, but they did not change the years. However, what they did do to the years is they have years since 1970. So it looks like for all of these years, we would have needed to subtract 1970 from the calendar year in order to create the model. Now we're going to assume that the conditions are met because that took a while, didn't it, to go through Liner. But we do need to know that L1 is going to be our date, or the number of years actually, since 1970. And L2, and this is from the Minitab output, they said, well, we're going to use a natural log. And so actually our L2 would be our Y values, but in L3, we would have the natural log of Y. But they've already done this for us and gotten the model. So my X values will be my date minus 1970. So that first one, 1971, that should come out as being a 1. And my transistors, which are in my L2, in order to get the transformed version, I would take the natural log of those. We're assuming Liner has been met. So, and from the output, I can actually write my model right now that my natural log, and I've already defined what Y is. So my predicted natural log of Y will be, so there's the Y-intercept on the constant coefficient, 7.0647, plus my slope, 0.36583, times my years since 1970. Just to be clear, when you're using a Y, you need to define what Y is. Now let's say we're going to use our model for a specific year. For example, if we decide to use this model for the year 2007, then let's put that 2007 into the model and let's find out what that would result in, and also how to solve for our Y, knowing that we're really finding the natural log of Y. So natural log of Y is 0.70647 plus 0.36583 times 2007 minus 1970. So that's really 37 years past 1970. And as I put that into my model, then what I find is that the value for the natural log of the predicted natural log of Y is 20.6. But how do you solve a natural log equation? We need to take the base of E on both sides of the equation because we're going to use the inverse. So so I have to hit the second key and then the natural log key, which gets me that base of E that I'm then going to take to both sides. So E, and then the exponent is 20.6. Then I can see that this number is 884 million, 28,623.9, but probably really 884 million is good enough rounding with the significant digits that I'm using. So look at my work. What's canceling a natural log is that base of E. And that's what I put into my calculator, E raised to the 20.6. And so then now my answer is 884 million, just checking the number. 884 million 884,028,623.6, but really your significant digits being 3 digits of 20.6. This is probably only accurate to the 880 million. But just to be optimistic, why don't I go with 3 SIGs and call it 884 million as my predicted value of Y. And that would be the number of transistors that we're predicting based on our model. So now if we want to use this model for the year 2025 to make a prediction, it's really outside of our X values and our data. So this value is going to be extrapolation and not really be appropriate use of this model. It might give us an idea, but it does seem to be a little bit away from our data, that enough of an extrapolation that I personally don't think that the year 2025 can really be predicted by this model. And it probably makes sense to you that it's really not appropriate to use this for the year 2025, because think about, we're in the year 2020. This data was stopping at the year 2010. So I have a hard time even imagining what's going to be happening 5 years from now. And can you imagine what's going to be happening, what would have been happening 10 years from 2015? So on another note, like if we want to look at the strength of this model for the data that we do have, that R is the square root of our R squared. So if we take the square root of 0.989, we can find out what R is. You have to decide if it's positive or negative, but it's positive 0.994. So this is a pretty strong model for the years that we have represented, but really outside of that, I'd say no. So now if we want to look at a model where we have logarithms on both the observed X and the observed Y, then we're looking at something called a power model. Please check out the example of a power model that I'm sharing with you that I saw in The Economist about luminosity and GDP. So this example is looking at distance from the sun and in astronomical units, which requires a bit of a conversion. And then it's looking at period of revolution, which is in Earth years, related to how many Earth years it takes to go around the sun. How many Earth years does it take? So this
So I've
this model is going to have logarithm
that
on
I've
both your
already
observed X and your
converted
observed
the
Y.
distance
So as we set up
from this
what this
potential
looks
planet
like,
that's bigger than Pluto,
X
I've
being
already
distance
converted
from the
it
sun,
into
Y being
astronomical
period of
units, which
revolution.
requires a conversion
Our predicted
of
value,
dividing the number
predicted
by
natural log for the
93
period of
million,
revolution.
and so that turns
Will
it into
equal
astronomical
our
units.
y-intercept
And I
plus
put
our
in
slope
my L1, which I took
times
the
the
logarithm
natural
of,
log
and I've
of the
put
distance
my
from the
y
sun, and that's
in,
of course
and
been
I've taken
converted into
natural
astronomical
log
units,
of the
which
distance from the
requires a
sun, the
conversion
natural log of the period,
to do
and
that.
by using linear regression on my L3 and my L4, I can come up with the equation, which is the natural log of the period is 1.499884 natural log distance from the sun plus the y-intercept of 1.6179 times 10 to the negative 4. And so that is the equation that the model that I generate using a natural log, which has a base of e. And then I want to take this model and I want to plug in the average distance for this new potential planet that's at 102.15 astronomical units, but it's really extrapolation, but we have a very strong model for this situation. And so we're thinking with this R value of 0.99999 going on, that maybe even though it's extrapolation outside of the Pluto, which was around 40 astronomical units, that, this is going to give us just a general idea of what might be the period of revolution in Earth years for this potential planet. And it kind of makes sense that like that kind of a relationship might hold true through extrapolation, whereas the transistors and the way we see technology changing, that extrapolation probably doesn't hold true. But in this situation, so I'm going to put in this situation being one that feels like it should work. Let's put that value of 102.15 into my equation. For some reason, it's having trouble writing. So when I plug that into my calculator, I get a natural log for the period of being 6.939. Plugging that into the calculator. But remember, this is the natural log of the period. So to get the actual period, I'd need to take the base of e of both sides of my equation. So e raised to this answer, and it looks like it would take 1,032 Earth years to go around the sun for this new potential planet. So think about how when you're solving equations, how in math everything has an inverse, and that inverse of the natural log is that base of e. So by writing it on both sides, I get to see that I can cancel the natural log and find that the period, the predicted period, notice my hat, is about 1,032 Earth years for this particular planet. And what's interesting is that there's a couple functions, and I kind of mentioned them, but just to show you that if you were in a situation where you just really didn't know what to do, there is exponential regression and power regression in your calculator. And a power regression would be where the calculator is knowing that it needs to do a log on both the x and the y variable. And so you can see that here's a power regression, and what it does is it rewrites the equation actually in base notation, um, so that this equation is actually kind of present in the real world. And that R value is for the linear regression of the log versus log equation, or natural log versus natural log equation. That strength shows you how strong it was, and then you can see that it gives you the the A value and the B value. You put those in this equation in the way it is. Problem is that that does not help you solve for the liner and look for the residual plot if that's what they're asking for in the um, problem. So using the model, using our calculator output, we could have written this model as 1.000161.8, and then our base of this model is the distance from the sun. That's our x. And then the exponent on that is 1.499884. And so this model actually is the calculator converting it to get rid of that base of e. It's already converted it into a form that then looks like this, so that you wouldn't have to do the conversion. So, and just to like show you something that's kind of interesting, because I'm making this recording because we are all doing online learning, and it's the time for COVID-19 days. So the Johns Hopkins University has a really interesting COVID map that shows like COVID-19 cases. It shows the deaths, the situation with how many have been contracted. And so on this day that I'm making this video, you can see the graph for this tracking the number of cases. You can see that it's definitely a curved graph, but you have an option on the John Hopkins website, and I hope you will look at this, where you can turn this logarithmic graph into a logarithmic graph. And what I can see is that the logarithmic growth, where it was very exponential, is now straight. In this particular model for the COVID, I would say that it probably could be explained using two separate models, like one model for this beginning part of the graph, and then saying like, okay, above a certain amount, we're going to switch to a different model. But again, logarithmic is what's making this kind of growth into something that's linear, that you